till now we have seen what are functional dependencies. Now let us see what are the applications of functional dependencies, or why are we actually studying these functional dependencies. So let's start with the application of attribute closure. Application of attribute closure. That means what is the benefit of studying these functional dependencies? What are the benefits of studying this attribute closure? So the first benefit is that we use them to find additional functional dependencies. Additional functional dependencies. Second benefit is we can use them to find the keys in a relation. When I'm saying keys means we are trying to find what are the candidate keys which are possible and what are the super keys which are possible. Third benefit is we try to find what are the equivalence functional dependencies, or you can say find equivalence of functional dependencies. And the fourth benefit is to find the minimal set of functional dependencies. Out of all this, we have already seen this one. Now let us see how to find keys in relation using the functional dependencies. Okay, now to find keys we are going to use the attribute closure, and using that attribute closure we can find what are the keys which are present in the relation. See, first of all you should know what is a key. Key means given a value of that key, you can determine every tuple uniquely. For example, if there's a detail about school, right? In school we can have the student, the name of the student, marks of the student, or percentage. So assume it is the roll number of the student, name of the student, marks of the student, and percentage of the student. Now we can have some data like this: roll number 1, name Himanshu, marks 56, and percentage is 23%. Roll number 2, name Akash, marks 29, percentage is 10%. Roll number 3, name Himanshu, marks 99, percentage is assuming 99% something, right? We can have some data like this. Now given some name of the student, you will not be able to identify the marks uniquely, and you will not be able to identify the percentage uniquely. But if I give you a roll number, then with the help of this roll number you can determine the complete tuple. This complete is called as a tuple or a record. You will be able to identify the complete tuple uniquely. That means you will not be having any kind of problems, right? That means the roll number should be able to determine name, the roll number should be able to determine marks, the roll number should be able to determine percentage. That means if there are 4 attributes in the relation, if I say roll number is a key, that means roll number should be able to determine all the other attributes uniquely, and obviously roll number can determine itself because that is trivial, right? So in the same way we can have some example of a relation. For example, relation R is having A, B, C and D. This is a relation with 4 attributes, and assuming that the functional dependencies which are given is A determines BC, B determines CD, and D determines AB. A determines BC, B determines CD, and D determines AB. This is the set of functional dependencies which are already given. Now first of all, let us try to identify what are the keys which are possible for this relation. See, keys means we are discussing about the candidate keys. Candidate keys are the keys which are minimal, plus they can determine all the other attributes of that relation. Okay, now you can take, for example, here A, B, C, D, there are 4 attributes, right? If I take A closure, then with the help of A closure, what are the things which we can identify? We can identify A. With the help of A, I can identify BC. Now with the help of B, I can identify D, right? So we have identified A, B, C, D, all of them. Okay, now if I take B closure, then with the help of B I can determine B, with the help of B I can determine CD, and with the help of D I can determine again A, right? So I can determine everything. In the same way, if I take C closure, then with the help of C I can determine C itself, but I will not be able to determine anything else. Now if I take D closure, with the help of D I can determine AB, and with the help of B I can determine C. So with the help of D closure I can determine everything. Now you can see there are few attributes, like if I take A closure, if I take B closure, if I take D closure, only with the help of A I can determine everything. Therefore A can act as a key. The second condition is the key should be minimal, that is a minimal set. Minimal set means if I take a subset of this A closure, then the subset is only 5. Okay, subset means proper subset. So if I take any proper subset of this A closure, that should not be able to identify everything, but you can see A is a minimal set which is able to identify everything. B is a minimal set which is able to identify everything. D is a minimal set which is able to identify everything. Therefore A, B and C, all of them can, we are having 3 keys here, A, B and C, all of them can act as a candidate key. Out of these candidate key, we select what are the other keys which are possible. Okay, what are the other keys which are possible. Okay, now let us look at the next example of this. Assuming that we are having the following relation R A B C, relation R A B C. Okay, and the given set of functional dependencies are A determines B and B determines C. So how do we actually find the keys? So you can say the set of all attributes that can be determined using a given set of attributes is called as attribute closure, that I already know. And if this attribute closure of a relation contains all the other attributes, then it is called a super key, right? And if the minimal set of that super key is called a candidate key. Okay, let me write it down here. You can say the set of all attributes, the set of all attributes that can be determined using the given set of attributes is called attribute closure and is denoted by X plus, right? So that we already studied, right? Now if this X plus contains all the attributes of a relation, then X is called as super key of R, as super key of the relation R, right? So where R is the relation. And now if X is a minimal set, then X is called as candidate key of relation R. The next is called as candidate key of relation R. Let me explain it to you what I have written here. If this is the relation ABC, then the functional dependencies are A determines B and B determines C. Now if I take A closure, right? So what are the things which we can identify? That is, A can determine A itself, A can determine B, and B can determine C. So we can determine ABC, everything. If I take B closure, then B can determine B itself, B can determine C, but B cannot determine A. If I take C closure, then I'll only get C because C cannot determine anything else. Okay. Now if I take some combination of these attributes, like if I take AB closure, now this AB closure can determine ABC. If I take AC closure, then this AC closure can determine ABC. If I take BC closure, then BC closure can determine only B and C. In the same way, if I take ABC closure, then ABC closure can determine ABC, all of them. Okay. Now here you can see this is the closure which can identify everything. Here we 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 can identify everything. But the problem is here this is representing a candidate key. it is representing a candidate key. Okay, candidate, you can correct the spellings, okay, so I'm not good with it. So it is representing the candidate keys, and these are not representing the candidate keys because this B closure cannot determine everything and C closure cannot determine everything, right? And here you can see this is representing a super key. So this is also candidate key as well as a super key, because super key is the key which can determine everything, and candidate key is a minimal super key. Okay, so you can say super key can determine all the attributes of that relation, and candidate key is a minimal super key, That means if there's a minimal set of this, or you can say the minimal subset whose minimal set means the subset of this set cannot determine everything, then that is called as minimal set. Okay, so let us take this example. Here you can see AB can determine ABC. Because it can determine everything, therefore it is a super key, but it is not a candidate key. Why? Because if I take the subset of AB, what can the subset of AB? The subset of AB can be phi, it can be A, or it can be B, or it can be AB, right? So if I exclude this one and this one, now this becomes the proper subset. Now if the proper subset of AB can determine all these attributes, then obviously it is not a minimal set. So you can see the proper subset of AB is A, and AB is determine everything. Therefore we proved that this is not a minimal set, because even if you take one single attribute A, that can also determine everything. Therefore this is not a candidate key, because candidate key should be minimal. It is a super key, but it is not a candidate key. In the same way, sorry, this is I did a mistake. This is not a key because it cannot determine ABC. Sorry. So here this is a super key, it is a candidate, it is not a candidate key. In the same way, this is a super key, but it is not a candidate key. Why? Because super key is because it can determine everything. It is not a candidate key because a subset of this, or you can say a proper subset of this, can determine everything. Therefore it is not a candidate key. Now further, this is a super key, it is a super key, but it is not a candidate key. Right? So roughly you can say, if this is representing the set of super keys, now why they are called super keys? Because they can determine everything. Then this is representing the set of candidate keys, because a minimal super key is called as candidate key. You can say the set of candidate key is a subset of the set of super keys. Okay, and we can have more than one candidate keys, and out of these candidate keys we can take one candidate key and we can make it as a primary key. Okay, so let us take one more example here. Assuming that the relation which is given to us is something like this. It is R A B C D. So this is the relation R A B C D. If I take the functional dependencies which are given are A can determine B, B can determine C, C can determine D, and further D can determine A. Okay, now in these functional dependencies, if I take A closure, then A closure is going to give us ABCD. If I take B closure is going to give us ABCD. If I take C closure is going to give us ABCD. If I take D closure, the D closure itself is going to give us ABCD. How I can give ABCD? Let me explain the first example only. Others are self-explanatory. So if I take A closure, A can determine A itself, but with the help of A, I can determine B. With the help of B, I can determine C. With the help of C, I can determine A. Therefore, I can determine everything. In the same way, for B also, with the help of B, I can determine B. With the help of B, I can determine C. With the help of C, I can determine D. And with the help of D, I can again determine A. So ABCD. Okay. Now, if I take AB closure, then AB closure can also determine ABCD. If I take BC closure, then BC closure can also determine ABCD. If I take AC closure, then it can also determine ABCD. If I take ABC closure, it can also determine ABCD. If I take AD closure, it can also determine ABCD, right? Or if I take any combination of these four, there are so many different combinations which are possible. So if I take combination of these four, like ABCD can determine ABCD, right? In the same way, if I say I can take any other combination like B, C, D, closure and so on. Now they can also determine A, B, C, D. Therefore all of them which can determine everything, they are the super keys. So these all are the super keys, these all are super keys. There are so many other super keys which are possible in this relation, and these are also super key. But out of all these super keys, only these 4 are candidate keys, or you can say only these 4 are the keys. Candidate keys are also called as keys only. So why they are keys? Because if I take a subset of A, then I will not be able to determine ABCD. If I take a subset of C, I will not be able to determine ABCD. If I take a proper subset of D, I will not be able to determine ABCD. But if you take these example, if I take a subset of any of these set, for example, if I take a subset of this, or you can say proper subset of this, then I will be able to determine everything. Therefore, it is not a candidate key, or it is not a key. It is a super key, but these are not candidate keys, right? So again, there's like this is sort of super key, this is a set of candidate keys, or we can have more than one candidate keys here. Okay, so let me take one more example. Assuming that we have the following relation. The relation is R, A, B, C, D, E and F, and the functional dependencies which are given, they are C can determine F, E can determine A, EC can determine D, and A can determine B. This is the set of functional dependencies which are given. Now they are asking which of the following is representing a key. That means number 1, option A is CD, option B is AE, option C is EC, and option D is AC, right? Which of the following is representing a key? Now you can see in all these 4 options, right, we don't they're just asking some of them may be a key, some of them may not be a key. Okay, so what is the easiest method of solving this? You can solve it in another method also, but what is the easiest method? If I take CD closure, then what are the attributes which we can determine? With the help of C, I can determine C. With the help of D, I can determine D. Now with the help of C, I can also determine F, right? And is there anything which we can determine? No. So we can only determine C, D and F. C, D and F. Okay. Now if I take AE closure, then what are the things which we can determine? With the help of A, I can determine A. With the help of E, I can determine E. Now with the help of A, I can determine B also. With the help of E, I can determine A, that is already included. Now is there anything else which we can determine? Here, can you determine anything else apart of this? No? Okay. Now let us take the next one. So it is EC closure. If I take EC closure, what are the attributes which you can determine? EC can determine EC itself. With the help of EC, I can determine D. With the help of C, I can determine F, right? And with the help of E, I can determine A. And with the help of A, I can determine B. So we can determine everything. So this is a potential key. Okay. Now let us take AC closure. If I take AC closure, then with the help of A, I can determine A. With the help of C, I can determine C. With the help of A, I can determine B. With the help of C, I can determine F. Right? Is there anything which we can determine? No. So this is not a key. So you can clearly see here it cannot determine everything. It cannot determine everything. It cannot determine everything. So because they cannot determine everything, therefore they are not representing a key, because key can determine everything. Okay. So and this is this EC can determine everything. But if I take a subset of this, for example, if I take E closure, then what are the things which you can determine? With the help of E, I can determine E. With the help of E, I can determine A. With the help of A, I can determine B. And is there anything else which you can determine? No, right? So in the same, if I take C closure, then you can see I can only determine C and F. I will not be able to determine anything else, right? So a subset of this cannot determine everything, but this complete can determine other attributes. See, there is one more way, there is one more shortcut of doing or solving this kind of questions, and that shortcut goes something like this. Check in the right hand side. Check in the right hand side what are the attributes which are not present, because we will not be able to determine them in any way. So you can see out of A, B, C, D, E, F, in the right hand side, C is not present and E is not present. All the other attributes are present. Now any candidate key or any key which should be there, they should include CE. Now if I take CE closure, and with the help of CE closure, if I can identify everything, therefore it will become a candidate key. But if it cannot determine everything, if EC closure cannot determine everything, then we have to add some additional attributes to them, right? So in that way, EC is not a candidate key, but if you add some attributes, they will create a candidate key. But if EC can determine everything, then if I add some attribute, then it will become a super key, it will not be a candidate key. Okay, so let us do one thing, let us take more examples of how to determine candidate keys for relation, and we'll take approximately 10 to 12 examples, and after that I think you'll be able to solve any question related to the determining candidate keys. Okay.